Okay, so what I'm going to do in this video is prove linearity of the Lebesgue integral of a simple function. So actually linearity um, for a general non-negative measurable function is going to be quite tricky, and it's best to just throw the big guns at it, and particularly uh, we'll um, uh, we'll use the monotone convergence theorem to prove it. There's just no reason not to develop the big guns, kind of like prove some of the big guns first, and particular monotone convergence theorem, and just use it. Okay, so remember we have this definition here. So if this is a simple function var phi, and we have the canonical decomposition of var phi in the sense that var phi of E are these distinct elements here, where EJ, and let's say rather EJ is the inverse image of each distinct element in the image, where these could be infinity, they could be zero, either way is fine. And we define the integral to be the sum, and in prior videos we motivated why this makes sense. And we had the following proposition. If we write my simple function on E in any way we want, as long as a linear combination rather of simple functions, or sorry, a linear combination of step functions, as long as the step functions partition E, then the integral is as you would hope, if linearity was true. So we definitely did, we're not being circular here. We definitely did not use linearity to prove this, because we don't know linearity yet is true for the integral of non-negative simple functions. So that's what we're going to prove right now. And to be clear, when I write integrals, I'm using this definition here. I'm using the definition of the Lebesgue integral of a non-negative simple function. Okay. So we have the following proposition. 1 second. Sorry, gotta make this a little bigger. Okay. So let's say I have two simple functions. And of course, always when I say simple, it's implied that they are measurable functions, and so is E. Okay, and let's say alpha beta is positive. Okay, so one, yeah, we have linearity. And it's a bit annoying to write, alpha var phi of x, and it's a psi, I think. So it's annoying to write x's everywhere. So I'm gonna, when it's annoying, I'm not gonna do it. I just like to do it, because my research involves Fourier transforms, and you know integral operators, where you're often integrating with respect to one variable, and another variable is kind of your function variable. So I just like to always make it clear what I'm integrating with respect to. But anyway, I'm not going to write it, but this means by induction that this holds um, for any finite number of simple functions. Okay. Two. So if A and B are disjoint, measurable, and if we define, so to be clear, I'm defining this. So it's going to be the characteristic function of A disjoint union B times var phi. This is a simple function, product of these two. Let it be clear. I want that. Right. So in general, if in general, if I have a subset of E, the integral over A of this would just be a characteristic function of A times this simple function. Okay. So this is saying integration against a simple function behaves kind of like a uh behaves kind of like a measure. We'll make that much more clear later on. And absolutely it will behave like the Lebesgue measure. Integration against non-negative function absolutely will have all the properties of Lebesgue measure, which is really, really nice. So again, to be clear, by definition, I'm saying that, I'm defining this as the following. Not sure how well the blue comes out YouTube, but so by definition, this is going to be characteristic function of A times this simple function. And the product of these two are certainly a simple function. Okay. Oops. Let's see how prove that. And okay. Yeah, so how do I prove this? So I'm going to prove one and the clever proof using proposition we just had. So let's write the canonical decomposition of var phi. So I'm going to write it CI, characteristic function of EI. And psi, write as some j equals 1 to m. dj, for lack of anything better, let's say ej prime. Okay. And yes, to be absolutely clear, I'm writing these, I want these to be the canonical. I want these to both be the canonical decompositions of my two simple functions, respectively. Because these are the canonical decompositions of my simple functions, and if you want to review what that means, I would watch either really of the prior two videos. But basically, the EIs and the EJs both partition E. These both are simple functions on E. And the CIs and the DJs are distinct. Great. I don't think we'll actually need that they are distinct, but that's okay. Yeah, so I equals 1 to n. And this is also j equals 1. Let's fix that a second. Pain, but whatever. This a little bigger. Okay. Yeah, so you can check, and I encourage you to check if you have any doubts. This means that for each I, EI can be written as this disjoint union. And the EIs and the EJ primes are all measurable, so everything's measurable here. Because we're assuming our characters, our simple functions, var, phi, and psi, are measurable. So j equals 1 to m, E, I intersect E, J prime. Actually, this is if and only if, but what's important for us is I can write, like, that means I can write my characteristic function as a sum of these characteristic functions. This is very easy to prove. If you have any doubts, you shouldn't, but if you do, definitely prove it yourself. All right, and the same thing for the EJs. For each J, I can write this. You might be able to see where this is going. It's really the same thing, except, sorry, for each EJ prime, except I'm summing over I. Here I'm summing over J. Okay. That means that this characteristic function here, same thing, is this sum. Right. All right, so we're going to put this to good use. So this gives us a way to write our linear combination of simple functions in a way that allows me to use my proposition. Okay. See how in a second. So that means that alpha var phi plus beta psi. And I'll probably put more detail than I probably should even, but that's fine. So strictly speaking, this is literally just multiply this by alpha, this by beta. I'm not really doing anything here. Alpha CI. This is J equals 1 to M. Uh, Beta dj. All right, so yeah, plug these two facts in. Plug this into here. Plug this, or rather plug this into here. Plug this into here. So just write it out of the sum, and you'll notice we'll get the same kind of sum. I equals 1 to n, alpha ci. I'm not going to write the parentheses. J equals 1 to m. Actually, I could just copy and pasted it, but that's fine. Similar thing. And I'm going to interchange sums in a moment. So, sorry, this is alpha here. So beta dj. E I intersect EJ prime. All right, so yeah, so I'm gonna bring this inside here, bring this inside here, and it's a finite sum. There's absolutely no issues with interchanging uh, orders of sums, even for infinite sums of non-negative um, stuff. You can always do that. Non-negative summons, stuff you're summing. Sorry. Thank you. But anyway, either way, this is sum I equals 1 to n, sum j equals 1 to m, alpha ci plus beta dj. All right. And the point is that, and this is kind of trivial just from this here, what I'm about to say, that all these sets partition E because of this. The EI is partition E, the EJ prime is partition E, and therefore E can be written as the disjoint union, I'll write it like this. I is in 1. I think I might get through this whole video without mixing up my indices. That would be pretty impressive. Um, I'll write this, whatever. So let me do this. Let me just move the bracket a tiny bit. Okay, so who cares? Well, I care because color to use. Lavender is a perfectly nice color, I guess. Right, so why do I care? Because I have my characteristic linear combination of characteristic functions written as a linear combination of characteristic functions here in a special way, and it's special because, and sorry, this is prime, because these partition E. And this is something you can check as an exercise. Again, it follows exactly from this here, which again follows from the canonical decomposition, both of these. Okay. So that means I can use this proposition. E is the disjoint union of all these sets. So there might be a whole boatload of repeats in these coefficients, but that is a-okay. Care. I guess start a new sentence. So by the proposition, what proposition? This proposition, right here. Okay, so by the proposition, this is going to be equal to the sum. It is easier to write as a double sum here, I think. Um, Probably, yeah, I'll just copy this here. Might be a little easier to do that. A little bit easier. Except here it's the measure uh, of these. All right, that's exactly what the proposition says. So let's call this star here, I suppose. Well, I don't have anything better to call it. So basically now all we do is go backwards. All I need to do now is go backwards. So this is going to be equal to, let's say I equals 1 to n. So I'm just going to break this up into two sums. Alpha ci sum j equals 1 to m. And basically the idea is we're going to get the two canonical decompositions with the measures of each EI and EJ respectively. Um, that's not clear, then it'll be clear in a minute. Okay. So here again, I'll switch it. J equals 1 to M beta dj. Sorry. I equals 1 to N. EI intersect EJ. Okay, but from what we have up here is a little messy, but yeah, let me start erasing some stuff here. This is definitely getting messy. Bear with me a second. Okay, that's good enough. Yeah, so we're going to use both of these here now. So this says the measure of EI is the sum of the measures of this over j equals 1, from j equals 1 to m. Same thing, EJ prime, the measure of each one of these is the sum I equals 1 to n of the measure of these. So it's measure of both of these. So we're just going to use this, plug it in to here. Yeah, and then we'll be done. Okay. Right. So, right, this is going to be equal to. So first of all, let me pull out the alpha. Why not? Well, I need to actually, I need to pull out the alpha. All right, so this is EI, beta, j equals 1 to m, um, dj, measure of E j prime. And well, these are the canonical decompositions of my two functions. Well, with the measure of EI and measure of EJ prime instead. But again, that is exactly the definition. This is the definition. These are my elements of the canonical decomposition of my simple function. Okay? If that's true, if this is the image over E where these are distinct, then the integral is this sum here. Okay? So I am writing canonical decomposition here. So by definition, this is going to be equal to alpha times this plus beta times this. Right. Um, yeah, there's actually really, if you think about it, there's no need to assume alpha and beta are positive. You can assume they're equal to 0, and this would also work. Um, yeah, you can assume these are non-negative. And that would work too. But anyway. All right. Yeah, easy proof. Um, so again, this step here utilizes these two. And then when I do that, I have literally pops out the definition of the Lebesgue integral of var phi and psi respectively. All right. So that ends the proof of one. Nice little easy proof. And I better plug in my laptop charger. Bye bye. All right. Um, yeah, so now two is extremely straightforward. Actually, knowing linearity makes a lot of things just super, super straightforward. All right, so they do. Okay. So remember what two is? Two is this here. Well, this relies on, we already used this fact above, so we don't need to say much about it. All right, so by definition, so remember we're defining this. So we're going to use the definition, uh, oops, sorry. Remember this is the definition, what this means. And you always do want to remember, technically, you can only integrate. If we have a function defined on E, you can only technically integrate that function defined on E. And you can make this a function defined on E by essentially restriction, or more precisely for us, just multiplying by a characteristic function. This is the definition. So we just proved using this. I'll do two steps here by linearity and one. I mean, I guess I'll even just use linearity in a second. All right, so we just proved that this is going to be equal to by one linearity. And again, I'm going to use the definition in a second. Uh, yeah, so this is a nice, easy proof. Okay, so that takes care of two. So three is a little, not tricky, but we actually have to do some work. Well, actually, sorry, there is no three. Okay, so next, what I want to, well, sorry, before I do anything, I guess I could have made a three. So I'll do another proposition. I guess that's probably the easiest thing to do. Move this over here, whatever. So if I have two simple functions, measurable, and point-wise, one is less than or equal to the other, then the integral preserves that, as you would hope to be true. Right. All right, so let's see how to prove it. It's a very simple proof, almost the same thing as what we've done before. Um, yeah, it's very similar to one. And yeah, I think at one point I thought about making it a homework, but yeah, so I do the same thing. I have my canonical decomposition of my two simple functions. Okay. So we're still going to use that. All right, so yeah, and actually rather what I'm going to do is I'm going to use this also. So I'm basically going to do the same thing here, except let me start erasing some stuff here. It was getting really crowded. So what I'm gonna do, um, yeah, so what I'm gonna do is I'm basically going to write psi in this way. So we're gonna get rid of the alpha, basically. Yeah, so I'm gonna write it like this. So I'll even do that right here. So I'm gonna combine this var phi rather, var phi into one sum I equals 1 to n, j equals 1 to m. Uh, what did I say? Yeah, I equals 1 to n, j equals 1 to m. So it's ci characteristic function, ei intersect e j prime. So let me move this over so I have more room. A lot more room. So I can write this, and I'm writing it to make things clearer. Might seem silly, but there's reason to do this. So I'm going to write this in the following way, ei intersect e j prime. So this here is simply going to be ci uh Well, it's basically just CI essentially. Yeah, so you can essentially just write it as yeah, I'll just yeah, I mean it's really independent of J, so for each J um it's just CI. Or if you really want to, you can write it like this. CI if E I intersect J prime is not empty, 0 if it is empty. Right. Right. And same thing, you can do the same thing for where is it? Yeah, for psi. So I'll do this in green. I'm going to do psi is going to be this sum here. So same thing. I'll even write it in green. J equals 1 to n d ij tilde sorry, times characteristic function. Right. Yeah, and I think writing it like this is going to make what I'm going to do a little clearer in a second. If you have any doubts, check. It's being redundant here because if if EI intersect EJ prime is empty, then that should be empty, not var phi. Uh, this. Yeah, if it's empty, then the characteristic function is 0, so it's just like 0 times 0. So again, writing it like this, I think is going to make things a little clearer. What I'm going to do in a second. Um, right. This is DJ. Make this a little bigger. This is not empty. 0 if it is empty. Okay. Right. So what does this, how does this help me? Okay. So one thing is, as I mentioned before, we know the EI intersect EJ primes partition E. So I can use my proposition. I'm going to do that in a moment. Uh, second. Right. Yeah. Yeah, so we have really two cases here. Um, so this is not equal to 0. Sorry, not empty. So for x in E I intersect E J prime, what do we have? We have Cij tilde is this here. We're assuming this is less than or equal to psi of x. All right. Well, the other case is trivial. Okay. If this is empty, then the same thing is true because they're both equal. So the conclusion is the following. For each I, j, Cij tilde is less than or equal to Dij tilde. So let's use the proposition one more time. So yeah, so I'm going to use the proposition twice. So it's actually two more times. Again, these, sorry. These here, these here and these here are non-negative. The EI intersect EJ primes, both partition A, sorry, partition E. So I can use my proposition twice. This is essentially Royden's proof with a ton of details filled in. Um, all of my proofs are basically Royden's with a ton of detail filled in. Okay, yeah, so using the proposition. So this is what the proposition says. I equals 1 to n. Cij tilde. Okay, so right now I'm going to use, so this is by the proposition. So that. Okay, but we just proved that for each I and j, this is true. So trivially, this is less than or equal to the following. It's the exact same sum, just replacing Cij tilde with Dij tilde. And we're basically now done. So again, by the proposition, this is the integral of. It's a little bit crowded, but I did go pretty slowly, so hopefully there's no issues. Um, yeah, so maybe one last thing, because it just yeah, want to do that. All right, so I think I'll end there. This is went on long enough. So I'll do maybe some further properties, and then we'll get into Chebyshev's inequality and then Fatou's lemma. So yeah, next video is going to be it'll be a shorter video, some further properties, and then I'll do one video on Fatou's lemma. So the next video will also have Chebyshev's inequality, which is super important. But all right, so long. Take care. Bye bye.